All right, recording on. Let's dive in. So this is kind of a monstrous lecture. So take breaks. I'll try to get us done in an hour and a half, but it can go long, or we may just sort of kind of finish early because the stuff at the very end is the stuff you guys have just seen in lecture. So sometimes people are like, yeah, I got that. So I'll do the best I can. This can be a little bit intense. So if you got to take a break, take a breath, feel free to get up and walk out. I'm just going to kind of try to keep a reasonable pace here. And the other thing is, this is just kind of a great PowerPoint or PDF to come back to. If you got to like review, let's say you go on to do more coding, grab this thing and keep it. And you can kind of jump in and scan through this quickly, and hopefully your memory will kind of come back to you. So, one way or another, it's a good kind of everything all in one place slide set. If you can kind of be like, yeah, I know that, or I'm kind of know that, you're going to be in a pretty good place. So, that was kind of the goal here. Stuff for the week. We talked about most of this stuff, so we're on our review lecture today. Tomorrow, if you're going to do your recursion lab 31, please get that one in. Appreciate that. And then if you need it, although many of you may not, you can do one of these two we talked about. Even if you don't need this, it's a great warm up before you take your next computer science class. So for example, if you're planning on coming to Comp 220 in the fall, I would suggest you do the binary search, but even the Dungeon Escape Revisited is really quite good. So very important thing to consider if you're going that way. Notes on the final exam. So have to be in class 11:10 a.m. is when we start. So come on in a little early if you like. We'll probably get kicked out of here promptly at 2 p.m. So if you start late, that means you don't get your full amount of time. So be aware on that. 35 questions, 2 points each, really just three essay coding questions. So it says 3 to 4 here, but there's going to be three. And you'll see great examples of those tomorrow at noon. That practice exam should be ready for you. And if we have time, we'll kind of touch on that today. No AI, as we mentioned. And please keep in mind that if you want to chat during the exam, you think it's a problem, whatever, you can chat to me on Zoom, but that means you got to be logged into Zoom. So find that link, please, before class, because often that creates stress for folks if they have a question and they can't come up. So appreciate that everybody kind of deal with communications that way so we don't disturb our neighbors. Your homework is 35% of your grade. I have adjusted points. So if you got an email from me already, it's just me kind of saying, hey, you still got 100%. Thanks very much for the great work you did. But I had to remove some bonus points just so you didn't go over 100%. And this is really just about a Canvas grading bug. I can't really find a way to get around it. So, all right, so let's dive in. We'll kind of skip over the first 15 lectures. You can always go back to the midterm video, but so much is based on what we learned already that most folks have kind of gotten this stuff under their belt already. One thing, though, we covered, I think it was starting around lecture 17, is the idea of binaries. So important, especially if you're coding in C++ and going on to do more computer science in general. Remember that when we count, we learned a long time ago, we're moving by powers of 10. 10 to the 0th power is like how many ones? There's 3 ones there. 10 to the first power is how many tens, and so on. We don't even think about it, right? So that's just how our brains are wired to work in base 10. But the same rules apply if we switch over to base 2, right? Or binary. And so because computers are built for the time being, before we get to quantum computing, they're built with binary bits, that's going to be base 2. So we're going by powers of 2. So it's 2 to the 0, still the ones column, always on the far right side, but you can only have 1, 1 or 0 ones. These are the symbols we're allowed to use in binary. There's 2 symbols, so we call it binary, right? As we said before, there's no symbol for 10 in our normal day of counting. We just have 0 through 9. That's 10 symbols, including 0. So we learned that we have to sort of think in powers of 2. But once we do that, it's a simple addition problem just to add up the columns where there's a non-zero value. And that is how computers are really storing their numbers. That's how they're storing music. That's how they're storing color. There is no place to store a picture in an image, or an image or a sound in a computer. It all has to be stored in these zeros and ones. And so it's all a matter of how we interpret a bunch of bits that are gathered together. So we got to know whether it's a character or a number. And that's why in C++ we've learned we have these data types. When we tell C++, hey, this is a character variable, it's like, oh, okay, so that's going to be an ASCII ID, as opposed to, oh, okay, that's an integer that we can do some math on. So those are little clues that help it know how to interpret these zeros and ones. But inside of the computer, they're still just zeros and ones, okay? And obviously more columns gives us more precision. So the bigger the number of columns in our data types, the more precision we have. So there's our character, right, with 256 different possibilities. 2 to the 8th power gives us 256. So that's how many ways we can kind of mix up those zeros and ones. So every data type has its own assigned size. Some data types reserve some of their area for the decimal part. So even though integers and floats in C++ have the same number of bits, the float type is floating, right? The decimal point can go to different areas automatically. And we don't have to worry about this. That's the really nice part about the float type. But the integer, the truth is the integer and the float can only represent a certain number of things. And in this case, it's 2 to the 32, because that's just how many bits we have, no more, no less. And the last thing we can do is go up to 64-bit, and we all have 64-bit phones, right? Maybe someday we'll have a 128-bit phones, but doubtful, because 64-bit is an awful lot of numbers. 2 to the 64 is a massive number, and it's enough to generally deal with almost everything except data security and encryption issues, and maybe flying past the current galaxy that we're in, right? But you can do almost anything you want with that amount of precision. So that's really what we're dealing with. That's why in C++, we decide ahead of time what kind of variable we want, because that results in using up more of the memory on our phone, or more of the memory on our devices that we're working with, okay? Now we can force these things back and forth in C++, either by assigning one type of variable to another, and sometimes that assignment works and sometimes it doesn't, but we can force it to work using this function called static cast. Now you don't need to memorize this function, but the idea of casting from one place to another is really about forcing those little numbers to either go into a bigger box and fill in what's missing, or go into a smaller box and chop off what isn't going to fit. So we kind of use the idea of mailboxes being different sizes, and that's kind of what this static cast is dealing with. So there's lots of rules. We won't go into them too deeply here again, but when we code, especially in C++, and we mix apples and oranges, different types, funny things can happen. So we always have to ask ourselves, what makes the most sense? If I have a really high precision number and a low precision number and I divide them, what should it be? Probably high precision. And that's really all we're kind of seeing with these little examples that we have here. So try to remember that, and just keep a little warning flag up whenever you're mixing and matching different kinds of variables. And especially if you're dividing int by int, you're not going to get a float. You're going to get an integer in C++. And different languages do this differently, so we just have to be aware of what the rules are, or be willing to go kind of look up those rules when we're curious about why our math isn't really coming out the way we want, okay? So that is called casting, okay? And this thing we've seen with the less than and greater than are called templated types. So that's really what static cast is. Again, we won't go into that too much here again, but we'll see that a lot. The more we work in C++, the more we see these little templated types. So that kind of led us into this idea of collecting things, which is really where computer programming languages start to do valuable things for us, especially data processing. So vectors, strings, and arrays are collections of things, but they manage those collections a little differently. Arrays are like primitive rocks and sticks, right? This is the most basic, low-level, simplistic way to collect things. These data types are kind of indirectly based on arrays, or the idea that arrays have, collecting things together next to each other in memory. So we sort of started out over here because these were like a little easier to get to know. If we make mistakes with these, we get some helpful feedback. If we make mistakes with these, we can just corrupt our data and maybe crash our program, or maybe just get the wrong result. So arrays can be very tricky, even though they're very, very fast. So we kind of saw that with the string and data type vector, we can use the methods. We learned later on that these are classes, and classes have methods, just like your car class that you design. And so we're saying string dot at position 0. We're asking the at method, of course, what's at position 0, right? So that is the method. And it turns out that the string can masquerade as if it's an array by putting these square brackets out there. So there's really two ways we can ask a string what's at position 0. And fortunately, the good people who wrote C++ said, well, let's just use the same idea for vectors. You can have two ways to get some information out of a vector. Now, if I create an array, this is a different kind of data structure, it's really primitive. I can only use those square brackets, right? So here are some arrays of different data types. Some of them have been initialized. Some of them have a dimension in there. We've talked about that. And so the thing we just got to remember is that our arrays do not have methods. They're primitive, old-fashioned. They're like a good old sports car, easy to fix. They run pretty fast, but they don't have a lot of safety features. And, if you like fixing old sports cars, you might like using arrays, right? So, and we don't even know how big they are. So they just don't know much. They literally are some spaces next to each other in memory where we shove some information in them, okay? So those are kind of our basic collections of information. Vectors could be anything, really. Strings can only be characters, right? And we know in C++ strings are double quotes, right? And characters are single quotes. Very important difference in C++. So if you try to put a character with single quotes into a string, you're going to end up getting probably a bug or maybe an error, especially vice versa. Now, I know it's confusing, but when we pass this information into a function, well, first off, when we declare the function or the prototype for the function, so we're not calling the function here. This is us saying, hey, this is the blueprint. You got to build this. We have to talk about all of the information about what goes in door number 1 and what goes in door number 2. So the name, we're going to call it, and what is the type. And so that I know caused a little bit of confusion because it's like, are we calling the function? No, we're actually just creating a blueprint. Later on, we may call the function, okay? So if this is our function with an array, right? Inside, of course, we just refer to this as a C, right? And we have this size, so we know how far we have to loop. So this is us going in, adding an integer value to the ASCII code. So this is really a character, but C++ does that magic addition thing. It's like, oh, you got a character here and you got an integer here and you're going to put it back into a character. Okay, I will just do that math for you and shift that essentially to be lowercase. So although we don't have to every day do this kind of low-level coding, it's important to understand that we can kind of move characters around the ASCII table by just adding values and then putting them back in. So in main, of course, we're just passing in the name of our array, which becomes the C up here. So name is this array here, right, in main, and we're just passing in, and it becomes the C in there, okay? So they are the same thing, essentially. In this case, the lowercase function is changing the array, right? Because our array, we could say, is mutatable by the lowercase function, okay? And just as this is just a a little hint. Notice that we get one free statement with our for loop if we don't add the curly braces. And if also gets one free statement that it glues itself to the if. So we can do a for loop with an if inside of it without any curly braces. And this curly brace, of course, just goes with that. But if you're in doubt, just go ahead and add your curly braces. It's always perfectly fine. Now, we said that vectors, as compared to arrays, are passed by value. So what we mean by that is, okay, this is a copy of whatever got sent in by main. So if we go ahead and just try to change this, we're just changing a local copy inside of this function. Notice we got a void function here. We're not returning anything. So in main, if I do this, it's not going to change the name in main. It'll change C in here, but there's no way for that thing to get back into effect main if it's a vector. That's just how vectors work. We pass it in here and it becomes a copy. Unless, as we said, we add the ampersand. And now we've said, hey, C++, these two things are connected. So if you change this, you're going to be changing that. That's what we call a reference. And that's why we added this would be passed by value unless we add this, and then it becomes passed by reference. So very often we'll see an ampersand before an argument in a function like that, and it's a clue that somebody is planning on changing that argument from the inside out. So that function is intending probably to make some changes to that thing. Okay. So that is how we pass by reference, but otherwise it's just going to be a copy and it will be passed by value. Okay. Important stuff. So high level, we can kind of see that when we create a vector, it's only as big as the information we give it. When we create an array, it can be bigger than the information we give it, and it just has garbage over here. We don't know what those values are until we actually initialize them. So we said arrays are kind of like ice cube trays. They always start at the size they were born to be, and they will always be that size. Vectors are a bit like accordions. They can get bigger or smaller as time goes on. You can add stuff to the back of a vector if you want, okay? And the vectors also know how big they are. Dot size will tell you how big that vector is, okay? So why use arrays? Well, they're faster, they're smaller, but very often vectors are your best choice, especially if you're working on something that has enough memory, you can deal with that kind of thing, okay? So two of our most important data structures. Now, if we really kind of lean into our one-dimensional arrays, right, we start thinking about really interesting things. And again, for those of you who are going to take Comp 220 or study computer science at some other school, algorithms is like puzzle problems. And very often we like dealing with puzzle problems with really simple data structures like arrays. Now, our string class here, just to remind you, collects characters, right? And we can even lock down a whole sentence so that it cannot be changed using our const char star. But if we want to have an array of characters, it's just going to be simply 10 spaces in memory, and then we can go ahead and do things with that. But for a lot of the stuff that we do in this class, we tend to just kind of put it in a string if it's a bunch of characters and go on about our business, right? Because that's probably the safest thing to do. We didn't really do a lot with this in this class, but let's just break down this array here. So I know it looks confusing. The stuff in yellow is what type of thing are we storing? The name, of course, is the name of the array, and this is how many things we're storing. So we kind of look over here and we go, okay, well, that looks like a string of letters, and this is a pointer. So what is this thing after all? Well, this array is really this. It's got 3 positions. Each position has a pointer. So we have to realize that it's storing pointers here. And each of those pointers is referring to one of these strings, Huey, Dewey, or Louie, okay? So we can slowly break down what these things are even though we might be still a little confused about that, we should be able to step back a little and go, okay, it's an array. It's got three things. What are those three things? It's whatever this is over here. And here's how they're initialized, right? So we at least know that position 0 has Huey, okay? So having those skills to slowly break down what you're seeing on the screen, even if you don't understand all of it, can be really, really crucial to helping you kind of get better at your coding. Okay. And then, of course, we can just kind of print this stuff out one by one and see what actually is at location 0, 1, 2, etc. Okay. So that's our literal string. And we said, there's some tricks that we can do with arrays in general. So we said this is just like a strategy. And this is used a lot. So we said that, hey, if you have some appointment days, and those days refer to day names, right? So notice my day names can go from 0 up through 6, right? That's 7 days, right? That gives us a way of putting an appointment day inside of the day name. So we said that that gives us the 6, right? Because that's that 6 right up there, right? And then if we drop the 6 into the day names, we get Sunday. So this is a strategy for looking up information by some ID. And we said that happens everywhere. Your social security number, your Moodle number, your VIN number on your car, all of these things are identifiers that can, if they're pure numbers, they can look up very easily a position in an array that then refers to you, let's say, or some instance of a class that describes you. So this is a strategy that, we slowly see more and more of, okay? So that was just something we learned about while we were looking at one-dimensional arrays. Then we moved on to two-dimensional arrays, and we had to learn about rows and columns. Row 0 at the top, row n at the bottom, or row n minus 1, let's say. And we said sometimes those things are referred to as matrices. But that sort of comes from math. But we always define them by saying how many rows first, and then we say how many columns. And if anybody tries to convince you otherwise, you should say, sorry, I don't want to speak with you. You're a crazy person. No, not really. But you'll save yourself a lot of trouble by just forcing yourself to believe that's the rows always and that's the columns. Okay. So this is kind of what we have in memory. So now we can position something at any location we want, right? Which kind of makes sense. We've all done kind of 2D graphs in grade school. So it's really kind of like that. We just got to remember that 0's at the top and the column numbers, right? Columns go across, right? So when we're looping, if we start with row 1 and then we loop on the inside, we're moving across the columns of row 0. So it's easy to get those things switched. But essentially, the outer loop for many of the things of code that we're going to write is sort of specifying first the row, and then we decide what column, okay? So that order kind of asserts itself in many, many ways in our code, okay? And we just got to remember not to go out of bounds, right? Or not to get our dimensions mixed up because we could crash, or worse yet, as I found in college, we could change the value of a variable and not crash. So I had the nastiest bug ever because I was overstepping my array, changing a variable in my own code, and it was going off, the deep end doing something crazy, but not crashing. And I thought I was losing my mind. So arrays are very dangerous in that sense because you can easily walk off the side of the earth and start mucking around in your own code, right? And changing things in ways that can be very, very hard to understand. Now, when we initialize our arrays, simplistically, we use that curly brace thing, and we saw we could use double pairs of curly braces and cosmetically arrange it so that it makes sense for humans. C++ doesn't care as long as you got commas between these things, right? But for us, we can sort of line it up the way we imagine a chessboard or something else, right? And if it's a string array, then I got to put some strings in there, okay? So that's the data type that's going in there. And that way, we now have somewhat of a picture of what we imagine that information really looks like. Now, the truth is inside the computer doesn't have rows and columns. It just has one long line of memory positions. But we can imagine this as being square for our purposes, rows and columns. So when we write a loop to initialize this thing, we're going to go slowly down the rows. So starting in row 0 and quickly across the columns. So we said that we start with row equals 0. And just remember, that's a 0, right? For the first time through. So if you're confused about this, just scratch that out and think 0. That's when I'm starting. Now, what happens, right? If we go across in that loop, the column is, of course, going to change, right? While we're holding strong on row 0. And that is one way to initialize our data array, our two-dimensional array here, is going across the row, or going across the columns quicker and going down the rows slower. Really, you could initialize it in two different ways, but why bother? Why not just do it the way most people do, which is going slowly on the rows and quickly on the columns, okay? So that is kind of how we actually do that. And in fact, that is also how we want to print out the information. So we said that, okay, assuming your array has something in it, let's print that out on the screen. And the all important ENDL, we have to remind ourselves that the inner for loop is printing across a row. And if we really want it to look like a row, we're going to need to move the cursor on the screen to the next line. So if we had stars in our first row 0, and we want to then move to the next row, we need the ENDL in there, okay? So we have to think about that as kind of coming after the inner loop finishes, but then we got to go back around and do the next row. So whatever is inside of our two-dimensional array will kind of get laid out nicely, okay? And we're just doing that for the humans. The computer doesn't care. It's just what we're printing, of course, on the screen so we can see what our data looks like. Or if we're Pixar or a special effects movie, we want to print out the colored pixels so we can see what the image looks like that was just created by the computer or ChatGPT or you name it, okay? So that is kind of never going to change, right? We're always going to be following a pattern like this if we're working from a two-dimensional array that has information in it, and we want to see it on the screen, okay? Now, the messy part about 2D arrays, or one of the messy parts, is passing them around. We got to do this silly thing. And it turns out that this can be flexible. If we want to pass in a hint about what that is, we can allow that to be kind of flexible. But we're stuck with this one. We got to like tell it ahead of time how many columns it's going to have. So this print grid function would work for any kind of grid as long as it has 10 columns. It could have any number of rows because we're just going to keep looping around the outside. And so for reasons that we won't kind of go into here, and so this is just calling the print grid. This is my prototype, right? So I'm saying, hey, just pass in that and the row count. And in this case, the row count is 2, right? 1, 2. But it could be that we had lots more rows and we could pass in a different number there, okay? So that's kind of some of the special things we need to keep in mind when we're working with these 2D arrays. But the function for doing the print is just going to receive the name, right? We don't pass in all of this other stuff around here, const or int and square brackets. We just give it the name. And then once we're inside of the function, we can then go to work with that information. Okay? So here's our print grid, right? And this is us going through, printing out what is at the row column location, right? And notice I got to go to 10 because it's locked at 10. But this one depends on what somebody told me. So we're going to go up to less than that, 0 to less than that, okay? So that is our kind of rows and columns kind of insights. And again, you will see this over and over and over again because we have spreadsheet data out there in the world. in the world, humans can kind of deal with 2 dimensions. Most humans struggle with the third dimension when it comes to data, right? And especially the fourth dimension, like don't even think about it, right? Most of the code that we're going to end up dealing with as beginning coders is going to deal with rows and columns. So if you got your head wrapped around that, you're doing a pretty good job, okay? Okay, so that kind of led us to pointers, which was usually the hard part for most C++ programmers. We kind of need to understand this to go very far in C++. So the most important first part is every variable has a secret address. So if I have the letter A, or if I have the A variable, that A variable is like a mailbox somewhere in memory that's holding on to a bunch of zeros and ones. Where is that mailbox? Just like a real world mailbox, it has an address. So if we want to know the address, we probably want to store it somewhere. So now we say, hey, this is going to be the address of A, or address of some integer, right? So now this is how we, of course, get the address of A. Pointer 1 gets the address of A, not the value of A, because A doesn't even have a value yet. We didn't really give it a known value, so it probably just has some garbage over there. But now we have the address, okay? And all of these ways we said are valid ways to create a place to hold on to an address. So an address, an address, an address, an address. What kind of address? An integer address, right? So that's all we're really saying here is this holds an address. What kind of an address? Well, an integer address. It's just some extra information designed to keep us out of trouble, okay? So that's how we start out finding the address of some variable, okay? Now, what do we do with that address? Well, once we have it, right, we can follow the address. It's kind of like follow the leader. You know, it's like, okay, you tell me to go to a mailbox, I will go to that mailbox and I will get what's at the mailbox. So get the value at an address is kind of like opening up the mailbox, pulling out the address of another mailbox, right? It's like, hey, go over there and get that piece of information. So we're kind of following a pointer, which is why we call that a pointer so often, which is really just pointing to this location. It's like, hey, go over there and get that thing. So Q equals dereference PTR is just going and grabbing the value at that location, okay? The flip side of that is kind of cool. I can say, hey, put the 10 at the location we're referring to here. So go see what I'm referring to and put a 10 there, right? So that's going to update that thing with a 10, right? So this line of code here is really going to put a 10 in there, okay? So these are the two crucial steps to moving forward in C++. We have to understand how to find the address of something and then how to use it to either read what's there or update what's there, okay? So those were our two primary things, okay? Now, so why can't we have just simple addresses? Why do we have to have an integer address versus a pointer address? Well, it's just C++'s way of keeping us out of trouble. Because as we saw earlier, we talked about the binary values. We could see that some variables are wider than others. So if we try to get an address of something small and then use it to access or store something big, well, things kind of break. So C++ is going to try really hard to make sure we never mix and match different kinds of addresses. So we can't, first off, we can't put a floating value in an address. That's only for storing addresses. 1.01 is not an address, okay? That could store an address, but we haven't put anything in there yet, right? Now we're trying to put the value of A, 1.0, in an address. That's also bad. We can't do that, right? C is just the same type as E, right? Int star, int star. So that's okay. So it's really just a game of apples and apples. Are we putting the same kind of thing in the same kind of box? Okay. So if the two boxes are okay, you can copy from one box into the other if they're the same. If they're different, then we can't do it. That's all that's really this is about. So the F box is a double star, and the address of the A box would be an int star. Okay. We say this, we get a pointer to an int, so that's an int star. So those are not the same thing. Okay. So it takes a little bit of practice, but just remember apples and apples, right? We want both sides of the equal sign to be the same type when we're making those kinds of assignments. Otherwise, you'll hear about it from the compiler. Okay? Now, this is so old, we probably don't even need this slide anymore. But whenever we don't know where something is and we're not sure what to store in a variable, we really should just sort of put the null pointer thing in there, nullptr. So in other words, hey, we don't want to have like, it's like having a bare electrical wire plugged into the wall, right? It's really dangerous. Somebody is going to touch that thing and get electrocuted. So we want to set that thing to null pointer. And that way we can test later on in our code, hey, if that thing's not null pointer, then I'll follow it and I'll put some value in that box. But I don't want to try to do that if that pointer is bad, right? So the null pointer is a way for us to have a signal or a test. We'd be like, hey, if this thing's good, okay, but otherwise I'm not going to mess with it, right? So that's really what our null pointer is doing for us, okay? So why do we deal with pointers so much? Because they let us do some things that are hard to do other ways. So here's an example of us getting the address of two different integers. So think of this as pointing to a mailbox over here and pointing to a mailbox over here. So the function doesn't get the value 4 and 5, it gets the address of that mailbox, right? So that it can go operate on the mailbox. So by giving a function an address, what we're really doing is saying, hey, we trust you. We trust you to do the right thing. I'm going to tell you where these two people live, and you can go swap what's in their mailboxes, okay? So A and B are the values. The address of A and B are, of course, just these values right here. Go find those things over there on, 23 State Street or whatever, right? So if I pass the address in, I'm going to assume that the function's going to make some changes for me, okay? And that's a really big assumption. Hopefully, that's not a malicious function that's going to do bad things to my data, but that's kind of the trust level that we actually have to deal with there. So let me clear away this scribbles here, right? So there's my values with their addresses. So we're passing in those addresses to enable that function to do what it's got to do, okay? So let's look at how that function is written. So using our basic skills and pointers in C++, we're going to say, hey, I'm going to grab onto what's at the first pointer. And that means I can transfer what's at the second pointer into the location of the first pointer, okay? So this is like safety zone. Put something in a safety zone and then copy over that with this. And then I can put this thing in there, okay? And that's a classic swap, okay? So we're just saying, hey, I got these two addresses. Now I can actually do this operation. It's like I'll put the 1 over there, put the 2 in there, right? And then I can put the 1 back over there and we're done, right? We didn't return anything. We got a void function. That means nothing's going back. All the changes are happening over here, okay? Get this thing off the screen. So that's our classic swap. And I know you're going to have some questions on your final exam about swapping. So the idea of swapping is important, but also realizing whether or not I've got a pointer here, because swapping can be done, as we'll see, I think, with references as well. Since we're on the topic of pointers, this is how we would do a swap given two pointers, okay? So you've seen this in your quizzes, I'm quite sure, so I'm sure you'll see it on your final exam, okay? So this is just another picture of what's going on in case it helps anchor your imagination. So I have a in main, and I have a pointer over here that's going to hold on to an address, right? So I pass in the address of A into the function directly. I don't even have a variable in main. I'm just saying, hey, here's the address of A. Go for that, right? Take that thing, pass it down into the function. Now this variable over here has the address of A, of course. So we say it's pointing to A, okay? Even though there's no such thing as a pointer in memory. It's just an address, but we call it a pointer so we can think a little more abstractly about it. But it really is just a number because everything has to be a number. But now we have our ability to follow the pointer and push the 20 over there. So our function is really working outside of its own domain because we gave it a pointer, okay? And that's one way that functions can make changes to things that they don't have access to directly. It's through these pointers, okay? So the understanding of these couple things opens the door to what most intermediate coders and advanced coders will start to do. Because your imagination takes hold and you think, oh man, I could make so many things, but I don't want to give everything a variable name. Like I want to make, a racing game with cars, or I want to model all of the viruses traveling around a petri dish, right? So that's just way too many variables. So we need to use dynamic memory so we can create things on the fly on this giant playground we call the heap. So we kind of said everything we've learned so far, those blue variable names, is really kind of automatic. We haven't had to really worry about creating or deleting them. We just sort of do it. C++ knows what we mean. And those things hang around inside of some scope, usually inside of some curly braces, right? After the curly braces, those named variables go away, right? So inside of those curly braces, we can use them. Different than that is our dynamic memory. Once we create it, it's going to stay around as long as our program is running. It's like loading the level on a game or visiting a web page in your browser. All of that structure has been laid out in memory dynamically, right? And probably there's not a lot of variable names for it. It's a lot of pointers connected to other pointers. So one way that we can create these things is with the new keyword. Create a new integer and give me the address of it, and I'll hold on to it somehow. Maybe I'll put it in a variable up here, or maybe I'll put it in some other piece of memory that I've dynamically created. Or give me 10 characters all in a row, and I'll hold on to a pointer to them. So notice that new always gives us a pointer. Always, 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 always. If I have a new, I'm getting a pointer, guaranteed, okay? So that means that wherever we put that pointer has to be a pointer type variable, okay? Now, we didn't really talk about static, and it's not going to be on the final exam. But if you go on to advanced C++ a year from now at College of Marin or somewhere else, you'll learn for sure about static memory variables, okay? But here's how we looked at creating data structures. What are data structures? They're just connections of pointers. It's like, hey, I would like to create something that looks like a tree, right? So I got to hold on to the foundation of the tree, right? The trunk of the tree. Well, what's the trunk? It's the address of the trunk, right? So the trunk in this case is going to be an integer. So I'm holding on to that integer. Now, I can't really grow that kind of a tree because the integer just can hold a value. But what if that was an instance of a class that had a pointer or 2 pointers or 5 pointers? So dynamic memory is used to create really interesting data structures that mirror the real world or some math problem or something. And so ultimately, we got to hold on to that address, which of that thing that might get more and more and more exotic. Okay. So in this case, we just have one little piece of information we're holding on to. But here is an array, and we will dynamically allocate information that we can hold on to the first location. We're really just holding on the address of the first, and the trunk of our tree sort of grows in that direction, right? We're creating 5 things. Okay, so that is a dynamic array, relatively simple. It acts just like a regular array. And eventually, like we all learned, as kids, we got to clean up our mess. So as coders, we got to do that too. If I created something with a new, I need to have a corresponding delete, right? Here's the pointer, go delete that, right? Here's the pointer that I created, go delete that, okay? So that is how we avoid having memory leaks and having our expensive memory, get wasted. And then for sure, it's always safe, like that electrical wire that's hanging out plugged into the wall. It's better to set it to null so nobody accidentally, electrocutes themselves, right? You don't want to follow that pointer off into some place there's no memory that you can use anymore, okay? So that's our new and delete, and it kind of opens the world for creating more and more sophisticated things. Here's an integer array, right? And then we can delete that thing. So we kind of saw that on the previous page, right? Setting that thing to null. And I think I would just pointing out that this is the correct way to do this, right? If you created it with square brackets and you want to delete it with square brackets, right? And then this is really where we want to go. We want to start creating a little more indirect data structures, kind of like a branch on a tree that holds addresses of other things. In this case, addresses of integers. So when I say array of pointers, 4 pointers, what kind of pointers? Pointers to integers. So when we did our, hunting for treasure and following those pointers, some of them were null, some of them were not. We were just following the address to some treasure chest, right? In this case, it's an integer, right? So here's some pointers. Only one of them has been initialized so far, right? These are all dangerous and garbage. They should be set to null, right? But in order to delete the item at position 1, right? 0, 1, we say delete what this is pointing to. So we're deleting this, right? Not this. We're deleting this down here, okay? And then we delete the whole thing, right? So sorry, my animations are a little off, but this deletes all of this. And then after we go out of scope here, this automatically goes away because it's our named variable. Okay. So tricky stuff, I know, but that's really the next level up, right? So it's okay if you feel a little bit queasy about that stuff, but the previous stuff we got to understand in order to kind of deal with this stuff. Now, we don't want to just have integers down here. We wanted to have more interesting things like cars and things and people and viruses and bank accounts. So that's where we got into object-oriented design. We said, hey, what if we could create our own data types? So instead of an integer, I could create a person or a smart car. And I could have pointers to those things. And I could have arrays with pointers. So this is where your creativity can really start to take off. It's like, oh, okay, the basic building blocks are pointers, arrows, and arrays, but I could create new kinds of things. So we said that a class is a container or a box that has things we call data members. So typically those data members are either going to be public or private. And that just means it's like, is it under the hood or is it in the driver's seat where you can access it? So private stuff is stuff like maybe your last name or, maybe there's some screw on your, your timing you want to adjust on your car that you don't want people messing around with, right? So that would be a data member and it's just a variable, but it's inside of every copy of a person, okay? So we have these data members and anything you could imagine that we learned about could be one of those data members. Arrays, strings, floats, doubles, you name it, Booleans, we've seen all of that stuff. But the weird thing is this constructor, this kind of robot that creates these things. We said a person is really a factory that produces a person or people. So we name the factory person, but really the thing that gets created is a person. And this often causes some confusion. You can kind of see I have a green person here. That's my constructor inside of the person factory. So when we call the factory and say, I want a person, we usually pass in some arguments so we can get a customized person. I want a person whose first name is Jeff and whose last name is Yates, right? For example. So, and there we go. That's the method that describes the person we've already created. So for every person, they not only have their data methods, but they have a method in the box that knows how to do things, like our smart car from our homework. Knows how to accelerate, knows how to turn the engine off, knows how to change gears. So every instance of a person can have some number of methods as well that process the information that's in the box with the person. Okay. So those are our methods and our data members, right? The key things that we want to remember when we think about classes in any language is that every class is there, every instance that we create is going to have some data members. The constructor is the robot that cranks out these people, these little copies of people. And then each of those copies of people also has potentially some methods in it that do special things. Okay. And that opens up the really advanced object-oriented aspects of modern day coding is creating descriptions of things that have abilities, like our smart car, okay, or an equation or a bank account. That's really where everybody needs to be able to go as coders is start to think about how we design object-oriented classes that do really fun or interesting or useful things. Video games use them, web pages use them, menu ordering systems for online food ordering use it. They're everywhere. Okay, and that's really what we want to do. And want to think about these instances just like variables. So integer a, double b, string msg, person Jeff. Right, Jeff's a variable. It's really a box. So this is a box with some information in it. It just has one thing, but this box can have any number of things inside of it. So we want to think of these variables as instances of a thing that have some additional intelligence, like a vector or a string or any of those other cool classes that we learned how to use before we learned really even what a class is. Okay. So think of that as the data type, and that's the variable name. And this is sort of our initialization value. And we said, oh, well, sometimes our instance doesn't need to have any arguments to initialize itself. So we don't even use those parentheses in C++. So if we don't give it anything, it needs to like figure out by default what its first name and last name is. Okay. Now, if we wanted to create these new instances without a variable name and just hold on to their address, we follow the same pattern we did with our integers, okay? So we say, hey, I need a new int, and here I've initialized that new int to 50. That's just a trick that we haven't really talked about too much, but it's just like we do with our string class, and maybe we put some arguments here for our person class, okay? So here I've kind of left the arguments out, but we are essentially just creating a new person over on the heap and storing a pointer to it in here. So the instance is over here, but we're storing its address, or the rover instance is over here, and we're storing its address. So new always gives us an address, and therefore we always have a variable that has the star in it, right? What kind of address? Rover. What kind of address? Person. Okay. So that's really what we're doing here. Okay. So if we wanted to use something that's object oriented, we can reach in the box using the point, right? Dot rather. Okay. So Jeff, in this case, is not, let's go back to Jeff on the previous slide. Jeff is a person. Jeff is not a pointer to a person, right? This is different. So on this slide that's coming up next here, if I want to reach inside the Jeff box, I'm going to say Jeff dot some data member, okay? Or Fido dot some data member. I don't know why Fido has a current row. So if it's an instance, use a dot, okay? Many languages kind of work with that dot, okay? And then we have our data member, okay? So reach inside of the instance drawer and get something, okay? So now, if it's a pointer, the tricky part about C++ is if it's a pointer and we want to reach inside the box, there could be multiple things inside of there. We're going to use the arrow. It's still reaching into a person box or a rover box or Fido box, right? But it's going to need to use the arrow because it's a pointer, okay? How do I know that? I kind of got to go all the way back to the definition of this and see, oh, what is that thing? Oh, it's a pointer. I'll use the arrow for that, okay? So you'll see some questions on the final exam about the difference between using an arrow or a dot to reach in an instance box. So just go back to the declaration. What is Jeff PTR? Let's go all the way back to Jeff PTR. Oh, it's a star. Therefore, I will use an arrow, right? Or Fido is a star, so I will use an arrow. That's the key difference there. I know it's a little confusing, but hopefully that illuminates it a little better, okay? Okay, all right, round in the corner into the end. We could create arrays of numbers. We could create arrays of people, okay? And in that case, it will call the default constructor, but those really are arrays of people. That really is a two-dimensional array of Mars samples. So we did this in our Mars rover homework. Every row column location gives us a sample, right? Every position gives us a person, okay? No star, right? There's no star there. So if I want to reach inside the sample, I'm going to say Mars 05 dot has tracks, right? For example, okay? But we can do that if we want. That actually puts the instance inside of the array, okay? So if I want to print from those arrays, right? There's our dot, right? So people 99 dot first name. This gives us a specific person instance dot first name. This gives a specific sample dot has water, okay? Again, we got to go back to the definition of people and Mars and go, is there a star? No. Is there a star? No. Therefore, we use the dot, okay? There's our dot for instances, okay? Okay, and there's our data member. So a little bit more on dynamic memory. So we looked at 4 major ways of creating an array as just simplistic data structures so we can compare. So here's a dynamic array of values. So the array is pointing to an integer. So this array is pointing to an integer, okay? It happens to also have some other integers there, but the only thing we're holding on to is the address of the first one. That's how arrays work, okay? This is an array that's pointing to a pointer that's pointing to an integer. Array that's pointing to a pointer, right? It's pointing to a pointer that's pointing to an integer. Array is pointing to a pointer, and that pointer is pointing to an integer. That's why we get the double pointer. Pointer, pointer. This is the first pointer, this is the second pointer, okay? That often confuses people. It's understandable that it would, okay? But if we wanted to do it with instances, it's really the same as 1 and 2 above, right? Array of foo instances or array of pointers to foo instances. Same kind of thing. Unfortunately, it's kind of just on the new line there. So star, foo, double star, foo, okay? If you can understand that one, you're doing great. It's a little challenging, but there's a lot of insight on that particular slide right there. I know we've kind of seen it before, okay? So let's just look at a couple more slides here. Hang in there. I know it's kind of reaching saturation here, but this is us creating an array of 4 instances of the number class and holding on to a pointer to the first position, okay? And that's me deleting all of that stuff. I didn't use it for anything, but I just created it and deleted it, okay? I'm saying go to, sorry about the color change, go to this address and delete all of the array that you see there, okay? And then maybe we'll set that thing to null, okay? Now, if I have something like this, I have two jobs to do. I can't just delete this because that leaves this floating around, okay? So you may very well see a question like this where you kind of need to loop through all of these things. And if something's not null, you got to delete that thing. And then you got to come back and delete this after that. So it's like one loop and then just one last big hammer to smash that thing and get it out of memory, okay? So this is us kind of creating that structure, right? So create that thing, hook up a new pointer, and store it in position 1, okay? And then if I want to know what's at that location, I just say arrow value, right? Give me that thing to print that thing out, okay? This is using our num class, okay? It's kind of a bit of an assumption we didn't put that num class on there. I'm going to kind of remind myself to add that here, okay? And then delete that thing and delete that thing. Okay. Okay, all right, so let's see where we got. Okay, destructors are just the cleanup patrol on your class. If your constructor of your class does something and you want to undo that thing, you can do it in the destructor. So the important thing to just take away at a high level is the constructor is the cleanup patrol for any mess that the constructor makes. The constructor isn't necessarily going to make a mess. So what you see here is just the constructor sending a message, right? And the destructor sending a message. So you kind of can understand when they're actually getting triggered. So of course, when we create a foo f variable, we're going to see hello, but the foo f variable is not going to go away until the very end of our program. And at that time, it actually triggers the destructor. So it gives us an opportunity to verify the general working mechanics of C++. It's like, oh, I just saw a goodbye from F. It just went away at the end of the program. Not surprisingly, because F is an automatic variable and it automatically goes away at the end of its curly brace scope, okay? So that's a really great way to kind of reaffirm what's going on with our variables, okay? So if I create something new, same class we saw, so I haven't created any instance yet of foo. I just have a pointer to nothing that will eventually be a foo, okay? So then I hook it up, right? And then I delete it. So in this case, when I actively delete foo, that's where we'll trigger the goodbye from the destructor, okay? So it happens when we say delete, okay? We just delete what this is pointing to, and it'll get rid of that thing for us, okay? So we kind of then went on to getters and setters, especially for our homework 7. So this was our kind of last homework for a lot of you. So getters and setters are just methods, but it's a tradition, you could say, that we sometimes call them get if they're getting information about the class, like its width and height. But if we're setting the width and height, we call that method a setter. So you don't have to call them getters and setters, but you can see here, it's a little more helpful, kind of helps me know what I'm actually doing. Get width versus set width, right? Set width, get width, okay? And in our case for homework 7, we returned a Boolean flag with our setters so that I could tell whether you had done the right thing. So we added the Booleans for our setters in homework 7 just so that I could kind of say, oh, you said you deleted it, but did you? I'll go check, right? So that sometimes makes the setter a little confusing But the setter's main job is to receive something and shove it into one of the data members, right? That's what the setter is really doing for us, is updating one of the data members, okay? And it's a convention, right? And it's separate from our constructors, and we could have multiple constructors if we want. You can call it with 2 arguments or with no arguments or some other combination, okay? So that was an example of our simple rectangle class, right? And we saw some of our things we computed. Not only did we get data, but we calculated some data like area or perimeter. So we can get something that isn't really just a data member. It's sort of computed based on the data members, okay? And so there's us using a dot. Again, I don't see a star here. So that means this is followed by a dot if we want to get a method or call a method or get one of the data members directly. Okay? And then there's us setting things and getting things. Okay. So we looked at a couple classes. We won't go too deep into this, but here's our 2 constructors. So you can call it with no arguments or 3 arguments that you want to provide, or you could assign default arguments to those constructor arguments. Okay. And here's all our getters and setters. Okay. Data members, constructors, getters, and setters, kind of laid out a little differently here. Okay. And then there's us creating a fan, getting its radius, setting the radius, etc. Okay. Stopwatch, we won't dig into this too much because we're not trying to turn you guys into time junkies, but you can do some pretty sophisticated things. And this is sort of was a warm up for our car class. So setting something might depend on other things, right? We don't want to change the gear if the engine isn't on. So a lot of logic inside of our instances or our classes deals with controlling or safeguarding so we don't do something dangerous. So a car was just one example of that. But think about a bank account. You don't want somebody to be able to withdraw money if they're out of money, right? So we don't want any negative values in the bank account. So different classes will have different logic for setting and getting different things, okay? And we can call these methods. So here our constructor is calling the reset method itself. So like any other function, we can call those methods from inside, okay? We saw also that we could pass these instances around. This is slowly reaching the outer parts of our atmosphere here, I know, for an introductory class, but just like we can pass in a number, we can pass in an instance of some class. In this case, the class is called number. So if I'm a number and I have a value, somebody could pass me another number and I could add that other number to myself, or I could add my value to its value and create a brand new third number that I will return as a result of the addition. Okay. So a number class can return anything it wants, a number instance or an actual integer value. Okay. Or nothing. So here we're saying add to me. Like somebody gives me a number, I take that number, add it to my own number, and just update myself. So notice I'm not returning anything there, but here I am returning something. Okay. So I should have called these things something different. Add and return and add to me. So I'm going to add myself a little reminder there to fix that, right? It should be 2 different names there, okay? Because it's 2 different strategies, okay? So down below, I would say C equals A dot add B. And over here, I would say A dot add B. Change A, okay? So this is a very powerful idea that we can sling these things around like hamburgers, right? It's got the bun, it's got the pickle, it's got the mustard, just passing the whole instance into the add method, and it gets taken apart inside the method and we do things with the different parts, okay? So that's a really super nice way we can start thinking at a higher level about adding What does it mean to add two instances together? Well, we'll figure that out inside of our function, right? That's up to us, the designers of the class, and how we want to interpret that. Okay. So if this was a Pokemon class, I don't know how to play Pokemon, but maybe you guys do, and you wanted to add two Pokemons together, right? There's some specific rules about, what happens, or maybe two Pokemons fight and there's an outcome, right? Like who knows, right? But all of the information would be passed in to the other via the other instance of the class. Okay. Super, super powerful thing to be able to do in our object-oriented way. Okay. And then we just said, remember, we can add default arguments to anything, constructors, methods, functions, but we still have to copy the argument into the data members of the class. Okay. So if we have these data members, if we have these data members right here, sorry about that, these are just values that we plan on copying in there. So really helpful thing. Most programming languages support stuff like that. Okay. So it just lets you do things that are a little easier to set up. So here is a constructor that has two constructors. So I can call the first one or I can call the second one. Okay. So here we have a default constructor and an constructor that requires one argument, but we could do it this way, right? And now we can call it like that, or we can call it with a single argument if we want, right? And so I didn't have that second argument there, but I could have said foo F1, right? Or I'll just say 11, so it's a little clearer. So that 11 would go into there in that case, okay? So those are some of the flexibilities we get if we just have one constructor with those default arguments. Okay. So the idea of overloading means we're just creating multiple copies of the same named constructor or method or function. That's all overloading means. Overloading means use the same name multiple times with different arguments, right? All of those are okay most of the time to live next to each other. Okay. The only problem we have is when we have a string and a string. That's going to be a problem. We got to just have unique function signatures for each of those constructors. Okay. Okay. All right, so let's see. Couple more examples. Here's a person that's pretty detailed class. So, whoops. Oh yeah, sorry, just more examples of the overloading. So I think probably you guys seen enough of that. Let's see how we're doing here. Lecture 27. So we're getting there. Got about 4 lectures. I'll go through this stuff pretty quick because I think we've seen a lot of examples of classes. But here was, first off, a reminder how we do swapping using an instance inside of a class, right? But here we're passing in a pointer to an instance. So what we really have, somebody gave us an address and it refers to an instance of a number over here. So this thing has a number and I have a number. So I'd like to swap its number, right? Its number with my number, right? So I'm going to put its number in temp. I'm going to put my number in it. So let's say we get rid of the 4 and put a 3 because I have a 3. And I will take its number here, right? Which used to be the 4. So this is one way to pass an instance by a pointer. And the way we would, of course, do that is just using our friend the ampersand. So a dot swap ampersand b gives me a pointer to a number, right? So the address of a number is a number star. So it all lines up, okay? So this is a method inside of our number class here, okay? So that is one way to actually access that inside of this method, okay? Okay. Get rid of my scribbles here. See if there's any more key information. How we doing? Gonna go a little long. Hang in there. So the nice thing about this is I'm just passing in the address, okay? Now here's another way to do that exact same thing in main. I know this is a little advanced for some of you, but notice what's going on here is I'm creating this over here. I've already got an address of something over here with a 1 in it, right? And I've got an address, I'm pointing to something over here with a 2 in it, okay? And then I just say, hey, here's your address, right? So I don't need the ampersand because this is already a num star. That matches my num star. So this and the previous slide are two different ways in main to create an instance and pass its pointer around. So here you can see I have an address, so I use the arrow. Address, so I use the arrow, right? And that's how we access that information. And then we can delete what those things are pointing to, right at the end, okay? So one more time, I'll just quick flash back and then we'll press on. So this was the other version, right? You can kind of see there's no new over here. So we had to take the address of B and we're using dots, right? Dots. But over here in main, we're creating it with a new, so we have a pointer, so we're using arrows, okay? That's the key. Okay, we're using arrows here, right? Hopefully that helps. I know it's pretty hard to keep all of that in your head, but that's the main difference in C++. Okay. Okay, now last thing is we could use references like we saw earlier on. We said we could put an ampersand in there and that gives us some power to change this thing. It's not a pointer, it's the actual instance. So it's linked magically via a different system, the referencing system, so that we can just kind of pass it in and have it swap that information, okay? So references are kind of like pointers. They're a little easier than pointers, less syntax to deal with. So if we pass it in and put that reference, it's just hooking this B permanently to this end. They're the same thing, okay? Kind of like a pointer, probably less confusing than a pointer, okay? Easier to change, okay? So here's some classes and UML. You're going to have a little bit of UML. I'll just flash over these quickly. But basically, minus means private, plus means public, okay? So private data member, public constructor, public method, okay? And the int is what type that data member is. And this is what type that is. And this is what it returns. Notice it's outside of the parentheses, okay? What does that return? It returns an integer, okay? So those are all of our key pieces. Just kind of a convention or another language used to describe a class, okay? Okay, we're getting down to it. 2 more to go here. Hang in there. We should get you out of here by 20 till for those of you who want to hang on. Const qualifier, we haven't done a lot with it, but it basically just locks in a value. It prevents us from ever changing X again. Why do we need a const? On large teams with new programmers, you're an intern, you get dropped into a giant pile of code. You want a const there for stuff you're not supposed to change. You don't want to accidentally create a bug. So the designers will make things a const to prevent you from accidentally blowing up the code. Okay. So we can make anything a const if we know it's not going to change or that it shouldn't change. Okay. And we can collect information from the user and put it into a const as long as the const gets created after we collect the data. That's generally okay. We create the variable secret right there, and now it's locked in forever. So const is just one way to actually do that, and it can lock it in at any point up until after the variable is created. Then we can't change it anymore after that, okay? Linked list, very important for all of you. Again, especially if you're going to our Comp 220 in the fall. So if we're going to link together two instances using our data members, we're going to first have to create those instances, and then we're going to connect them. So if we have a next variable or data member in each one of these classes, initially it's going to be none. But if I copy this address that's held in this pointer and put it in there, we say that now this thing is pointing to the same thing that this is pointing to, right? I stole this address and put it in that little next there. So wow next gets the address of this pointer, and now we've modified this so that they're connected together, okay? Now, obviously, they don't move around inside of memory, so we're just doing that to help us visualize a straight line, which is really what a linked list is. It's just about connecting things together so that in the memory of the computer, we can follow all those pointers around. So it's clearly not in a straight line in the computer, but that's the way we access them, in a straight line. That's why we call it a linked list. And it's one of our fundamental data structures. Vectors are probably using some form of a linked list in an array, some combination of those things together. So if I want to add something at the head, and this will be important. So remember, first we got to create the thing. Then we want to hook that oops up to the LOL. So I have to say temp next equals head. Okay, that's how we hook that thing in. And then we just update the head. And now we really don't need temp anymore. We've kind of inserted a pancake on the top of the stack. So as you may recall, if you just keep adding another pancake, the stack is kind of in the reverse order that you put the stuff at the head. Sometimes it's a surprise, but that's generally what happens when we push another number at the head. We kind of reverse the order that we put these things in. If I want to delete from the head, similarly, I'm going to grab onto the thing I want to delete. I'm going to move the head around it, okay? So I'm going to say head equals head next, or head equals temp next. Those are both the same thing. Move the head to the head next pointer. If this is head, then this is next. If this is temp, then this is temp next. So it's the same thing. Head equals head next, or head equals temp next. It'll take you around that thing, okay? And then we can return the text from that temp and delete the head, okay? And now it's going to go away. Delete temp, or sorry, not delete head, delete temp and return the string. So that's inserting at the head, deleting at the head, okay? Now, if we're going to delete from the tail, it's tricky because in order to delete the last thing, I have to stop here and then use this thing and set it to null and delete this thing here. So I don't want to go to here, and I certainly don't want to go to here. So my while loop is going to need to search for the second to the last thing. So that means keep going while temp next is not null. Because if temp next is null, that means we found it. We are here. If temp next is null, then we are at the right place and we don't want to search anymore. We just want to do our work and go home. Get rid of that thing, get rid of that thing, and off we go. So we would copy the string, delete the foo, nullify the pointer. I don't know if that's in there. We need to fix that. We need to say temp next equals null. Is that in there? Nope, I don't have that in there. I should put that. That's an important part of that step there. Okay? Otherwise, we'll have a bug. Okay, so that's deleting from the tail. Okay, now deleting from the delete from the tail of a linked list. General case, right? Exactly. Now, special case is you got just one thing there. So what if you got one thing? Well, we don't need to loop at all. It's really easy. We just copy foo, and then we're going to set the head to be null, right? And delete that particular instance of the class. Okay. So these are the basic things that we do with linked lists. So if you go on to more advanced stuff, we will do more advanced things. We'll cut things out of the middle. We'll insert stuff in the middle, but deleting from the head, deleting from the tail, and inserting at the head and inserting at the tail are kind of the main operations that you need to be familiar with in this class. So they're fortunately in the quizzes. So if you're able to practice your quizzes, then I think you'll probably have what you need to kind of do well on the final. Last major thing, or one of the last major things we talked about was recursion. So recursion, we're saying, is just functions calling other functions. So this is not recursion because we did a silly thing here. We wrote 3 different flavors of the same function, right? And so no one is going to try to do that for factorial of 100. But we realize that C++ has a secret power. It can make copies of functions automatically. So if a function calls itself, it's going to make a copy in memory and wait around like a bucket brigade for the information to return from the very bottom of the stack. So our dig thing was all about learning how to stop, right? So here's us continuing until we trigger what we called the base case. We finally get to some condition, which we generally test right away. And I say, hey, don't keep going, just return, right? This would keep going deeper and deeper. So our base case for recursion is really the most important part of recursion, because otherwise we have an infinite loop. We just go on and on and on. But otherwise, we're returning little pieces of a bigger problem. And slowly but surely, they get added up or multiplied up to actually come up with some bigger answer, like in this case, maybe a 6. So recursion is about going down and coming back up again. Both of those things are so important. Now, sometimes recursion doesn't return anything. So here's us calling ourselves to print what's at the last position, position X in this string, and then changing what the last position is to be more to the left, closer to the beginning by 1 every time. So this is one way to return, or not to return, but to print things in reverse. And the last thing we do is just go home, right? But we're going to unwind through all the levels of the mine shaft that we came down to get back to the surface. That is always going to be the case, okay? Even if we have a void function, we always are going to return through all of the levels. It's like going down an elevator and coming back up again, okay? So if we try to return a string, this was the more complicated example, we're going to have a data type for the function that says what we return. We're going to return a little piece of the letter that will glue on to the next thing and the next thing and the next thing. So this was the other example we looked at. Okay. And then for some of you who decided to do the lab, doing an infinite series is kind of applying this idea to math. We're just saying, solve a little piece of the problem, right, by calling a previous version of the function, right? So get this for some other term and then add it to this term and then return it, okay? So we can solve some really fascinating problems. Some of you might have recognized that if you went deep enough, you could eventually find the answer to things like square root of 2, right? Through iterative solutions. So if you like math and you like physics and you like, you know, that kind of stuff where you solve really hard problems with your computer instead of your brain, or maybe things that your brain can't solve, you actually can do that with recursion, okay? Whew. Okay, so that is the stuff. So I'll kind of leave it there. I know we ran long. Thanks for staying. I'll hang out if you have any questions, but otherwise, no lab. And we'll see you on Tuesday at our normal time in here. Please don't be late. I'll send you a reminder. I will be around on Monday in my office. If you want to come by for any discussions about grades or anything, just drop me an email. Otherwise, thank you. Good luck. And I will see you guys, I'm sure, before end of the semester. Okay.